Hey, good afternoon, everybody. My name is Partha, and my topic today is about IP addressing in computer networks. This is one of the absolute foundations of how the internet works. So, in this, we will cover IPv4, which we use every day, both the classful addressing system and the modern classless approach using CIDR and subnetting. We'll also learn about IPv6, understanding why it exists, and we'll look at network address translation or NAT, which is the clever workaround on which that's kept IPv4 alive despite the address exhaustion thing. I'll come back to that later. So, hopefully by the end of this lecture, you will understand how devices get their addresses, how networks are organized, and why we're slowly transitioning to IPv6. So, first off, let's just start with why IP addressing matters, right? Why do we even care about IP addresses? So think about the internet. Okay, there's like billions of addresses. Okay, phones, computers, servers, cameras, sensors. All of them need to communicate. But like, how does data know where to go? Uh, we use these. Like, they sort of use like postal addresses. Here, this is called. They use sort of like postal addresses. These are called IP addresses. Okay, these are for the internet. So your device needs like a unique address, so the packets can like receive it. Okay, routers use these addresses to forward data to the destination. So without IP addressing, like we wouldn't know like where to send which data and where to receive. Okay, there'd be no routing, and the internet, as we know, basically wouldn't exist. Okay, so beyond the internet, IP addressing also lets us organize networks logically. We can group devices into subnets, apply security policies, and manage network resources efficiently. So IP address is literally the foundation that lets any network function. Okay, so there are two main versions of the internet protocol that we care about. So IPv4 here. Okay, this was designed in 1983, like 32-bit addresses and dotted decimal notation. Okay, but the problem was that it only gave about like 4.3 billion addresses. It sounds like a lot, yes, but in today's world, it's nearly not enough. It's about to be exhausted. So now we are slowly shifting towards a new protocol called IPv6. So this was introduced in 1998. So again, they have just tried to expand it. That's just it's just an expansion problem, right? So this was made in 1998. This uses 128-bit addresses with hexadecimal notation instead, along with these colons. I think I've put another example here, 2001. So you get the idea. Okay, so this had roughly about 340 undecillion addresses. I mean, 4.3 billion is a lot. Don't get me wrong, but 340 undecillion is like quite a large margin. Okay, so it's safe to say we won't run into this problem, at least not for the near foreseeable future. So this is probably what we are going to use all the way. Okay, it's enough for every person on the earth to have more addresses than the sand. Uh, so, but we also have something called as NAT. I'll explain it later. Okay, which still helps us to like sort of stretch IPv4. Okay, I have introduced IPv6 and I will be going on it, but our curriculum mostly talks about IPv4, so we'll mostly focus heavily on that. Yeah. Okay, so now I want to talk about the IPv4 address structure. Okay, so in here, an IPv4 address is basically it's split into 32 bits, which is divided into 4 octets of 8 bits each. Okay, and each of them are separated by dots, as you can see here. I don't know if you can see my cursor. So again, looking at the binary, this one you can already see it's like 11000000.101. It's along this one, but you can see that each like octet, okay, it can represent any number between 0 to 255. Okay, now the important part is that every IP address here is divided into two portions. Okay, there's the network portion and the host portion. Now the network portion, this identifies the network in which that device belongs to. Okay, and the host portion identifies the device itself on that network. Okay, So let's just take, I put an example here, right? 182.168.1.100. Okay, so maybe the first 3 octets, okay, are the network, and the last octet is 100 is the device. Okay, but like how do we know what is split? Okay, so this 168.1, okay, this depends on the addressing scheme. Okay, whether it's classful or classless. Okay, I'll show you that. Okay, so diving into this. Now, for many years, we used classful addressing. Okay, we basically just divided all the IP address into fixed classes. Okay, based on the first octet. Okay, if you look here, I'll show you class A. So the first bit here, I think I've linked an image. Okay, this was 0. The range of the bits were anywhere from 1 to 126, and it had about 8 network bits. Okay, this could support about like 16 million hosts per network, which is huge, and everything sort of like goes, it's going a little bit down and down from there. Okay, then here the first bits here are 10. Okay, you have it ranging from all the way from 128 to 191. This one, the network bits were 16, but the hosts per network were about like 65,000 or above. Okay, class C being 110 first bits, you have 192 to 223. Okay, and network bits were 24. See here. Okay, so you see how the bits are slowly expanding all the way from single bit in class A, 10 in class B for the first bit, and 110 3 bits for class C. Okay, and but this could only support like very less. Okay, this is about 254 hosts per network. Now class D and E, they are reserved. Okay, so D is reserved for like multicache, and E is for like any future use that we'll have. Okay, but the problem was that classes were rigid. Okay, if you need 1000 devices, like you need a class B. Okay, which will give you like 65,000 addresses. Okay, sure, you're using 1000, but like what about the remaining 64,000? Okay, it's like such a massive waste, right? Okay, if you need like 500 devices also, you need multiple class C networks, which is like fragmented. Okay, so this is not very efficient, right? So then we came up with the idea of classless addressing here. Okay, before we move on, I just want you to know about these like private IP address ranges. Okay. So these are special ranges that cannot route on the public internet. They are reserved for like internal networks. Okay, you have class A private range is from like 10.0.010 to 10.255.255.255. Okay, again these are all ranges. Class B private is from 172.16.0.0 all the way to 31.25. You see how it ends at like 255 for each. Okay, this is how it is. Okay, so you have class C. Okay, and your, I mean, you've probably definitely seen these. Okay, your home Wi-Fi router probably gives you device addresses. It will give you like the 192.168.xx whatever that range is. Okay, anything with it. Office networks might use like 10 point something something something. There are also like special ranges like these loop back ones, 127.0.0.1. Okay, this always refers to your own machine. Okay, this is used for testing. Okay, we have link local, which is this 169.254 something something. So this is assigned automatically by devices when no DHCP is available. Okay, so why do private ranges exist? Okay, the internet would collapse. Okay, if every device needed like a unique public IP. Okay, so instead, like organizations, they just thought, hey, why not? We don't need to show it like right away for testing. Okay, so we are using private addresses internally. Okay, and we use a technique called NAT. Okay, this translates them to public addresses when communicating in the internet. Okay, so yeah, I've come back to classes addressing now. By the 1990s, the rigid class system was causing problems again, like I mentioned before. So the internet community invented classless inter-domain routing, or this is called CIDR. So instead of like fixed classes, okay, CIDR lets you specify a subnet mask. Okay, so this can be any boundary that you like. Okay, the notation again here is just IP and prefix. Okay, so let's just take 182.168.1.0. Okay, So this means that the network address again is 192.1.168.1.0. The subnet mask is 255.255.255.0. Okay, this is the first 24 bits, the identifier network. The last 8 bits are for hosts, okay, allowing for 254 usable addresses, like I mentioned. Okay, but the beauty of CAD here, you can create networks of any size. Okay, you can make it 30, 4 addresses. You can make it 20, 4096. Okay, 16, 65,536. Okay, like anything that you need, whatever you need. So this flexibility revolutionized internet addressing, like at that time. Okay, when IPv4 is still prevalent. Okay, so subnetting basis. Okay, so often we need to take one large network and we need to break it into smaller pieces. Okay, this is called subnetting. So let's just say you have a company with a main office. So let's just say the main office has 100 people. Okay, and the branch office has 50 people. Okay, you might take the original network, the 192.168.0.0/24 network. Okay, and we can subnet it into /2/25 blocks. Oh, by the way, I'll teach you. Okay, so to subnet, okay, we increase the prefix. Okay, so let's say /24 to /25. Okay, this doubles the networks and it halves the hosts. Okay, so this is how we are like splitting, by going up the prefix. Okay, so here you see where 168.0.0/25, this is the main office. Okay, and 0.128 at this branch office /25, this is the branch office. Okay, so why subnet though? Okay, so here we can reduce broadcast domains. By broadcast will stay like local, they will say bandwidth. Okay, you have better security, you can apply like different firewall rules to each subnet. Okay, so this way you can individually protect according to their needs. Okay, you have efficient allocation, so everything gets exactly what they need, and you have organizational clarity. This, like the network structure, it mirrors business structure, so this helps it a lot. Okay, it's very useful. Yes, so now we've come to IPv6. Yes, this is what we are adopting in the future. So instead of using like 32 bits, okay, we use 128 bits. Okay, here there's 8 groups of 4 hex digits. Okay, look at this full form is look at this one. Okay, so you have 2001:0 DB8. Okay, so each of this is one, like 4 hex digits. Okay, each of this is one group. Okay, so you have about 8 groups of these. These make one IPv6 address. This is what one looks like. And again, there is a compressed version where we put double colons together, because again expressing this is like pretty huge. Okay, so here the first 64 bits is the network prefix, and the last 64 bits is the interface identifier. Okay, 120 bits is again truly enormous. It solves, it basically addresses every exhaustion problem that we have forever, and it allows every device to have a globally unique routable address. You don't need any NAT, nothing is needed. Okay, so why IPv6? Okay, so again, like I was explaining, so IPv4 addresses are depleting, let's be honest. Okay, by 2011, IANA, so this is the central authority, they ran out of IPv4 addresses to allocate. Okay, so this rush is caused by the Internet of Things, the IoT explosion. Okay, so today we have billions of smartphones, right? We have smart home devices, we have washing machines, AC, some even cars. Okay, so IPv4 is 4.3 billion addresses. Okay, simply aren't enough. Now IPv6 though, again, like I said, 340 undecillion addresses. Okay. Even if you allocated one address, okay, to, like I said, sand, okay, you'd still use like less than a trillionth of IPv6 address space. Okay, it's so minimal. Okay, adoption is growing but slow. Okay, changing the core internet infrastructure takes like decades. Yeah, so we have network address translation. This is currently, so still we're slowly in the adopting phase, right? So what to do in the meantime? Network address translation, or NAT. Okay, so NAT is like a clever workaround that translates private IP addresses to public IP addresses and back. Okay, So how it works? Okay, so let's just say your router intercepts a packet from a private device. This 192.168.1.100. Okay, so it rewrites the source code to its public IP. Okay, like say 203.0.113.4. Let's just say something, and sends it to the internet. When the server responds, the router translates it back to the private device. Okay, so there are like about two types of NATs. Okay, so there's a static NAT and a dynamic NAT. So static NAT is just one private IP and one public IP. Okay, it's just one to one. Okay, but dynamic NAT, okay, this provides multiple private IPs to a pool of public IPs. It's multiple. Okay, and we even have PAT. Okay, so port address translation. This is an extra. Okay, so many devices share one public IP using different port numbers. This is what your home router does. By the way, you have multiple here. I'm showing you with this router. So this is an example of PAT, port address translation. Right. And here again, this is exactly what I've explained in the previous session. It's static, dynamic, and PAT. Okay. The advantages, obviously, it extends IPv4 life indefinitely until we swap over to the newest one, and it adds a security layer by hiding your private network. The problem is that it breaks end-to-end principles. Okay, the internet was designed so any device could initiate a connection with to one another. Okay, so NAT breaks that. Okay, it adds latency. Every packet must have to be translated in order to be understood. It breaks some protocols. Apps like older like VoIP or FTP, they don't work that well in NAT anymore. So older apps, there is just no compatibility anymore. Okay, but still at the end of the day, the real reason for IPv6 is that NAT is basically a band-aid. Okay, this is just holding it in place, barely holding it in place, right until we switch over to IPv6. Okay, IPv6 again, we already saw it. It almost eliminates every problem that's there. Okay, but until then we are being held together with NAT. Okay, but it's still important that you know that there are these trade-offs. Yes, so we have come to the end of this. To summarize, we have IPv4. Okay, we are going through the evolution, how they first came to this. Okay, so they first wanted to make unique IP addresses. They brought in IPv4. We started with classful, this rigid this one, and we evolved to classless. Okay, for flexible allocation. Okay, then we went to private ranges for companies. Okay, so these are for internal use and they cannot be used routed with the on public internet. Okay, we looked at subnetting, SCIDR. Okay, where we use prefix lengths like /24 /25. Okay, to organize networks efficiently. And we have the ultimate, final, that we have IPv6. So this is 128 bits. So this is future proof. Okay, we will, for like a very 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 long time, we are not going to have any problems whatsoever. Okay, there are unlimited, we can say it's unlimited space. Okay, and this is the future standard. Okay, and we have NAT. So NAT, until we fully transition up till IPv6, we have NAT, which is extending IPv4's life by allowing private networks, but it adds latency and it breaks some protocols. And yes, so thank you. That's it for IP addressing. We have covered everything so far. We have covered the evolution, and I have shown you. I think it's pretty cool seeing how they've gone so far, all the way from 1983 to 1999. And we will still be continuing with this IPv6 in the future. But yes, thank you.